Good morning, my dear students. Today we are going to see the definition and examples of open and closed sets in a metric space. First, we start with by providing the definition of open ball in a metric space. Let x comma d be a metric space and small x belongs to capital X and r greater than 0. The open ball centered at small x and radius r is defined by b of x comma r is equal to set of all y belongs to capital X such that d of x comma y is less than r. Here, the open ball centered at x and the radius r not only depending on the whole set capital X, it also depends on the metric d. From the definition, we note that it is possible to have different metrics on the same set. To make it clear what metric is being used, the open ball b of x comma r in a metric space x comma d can also be written in the form b suffix d of x comma r when the metric that is being used is not clear from the context. Examples for open balls. Consider x is equal to the set of all real numbers r and the metric d of x comma y be the usual distance metric. Then the open ball centered at small x and the radius r is given by b of x comma r is equal to set of all y belongs to r such that d of x comma y is less than r. Using the definition of d, set of all y belongs to r such that mod x minus y is less than r. By using the definition of modulus, we find that the open ball centered at x and a radius r is equal to the open interval x minus r comma x plus r. Second example. Here again we consider x to be the set of all real numbers, but the metric d we consider the discrete metric. That is, d of x comma y is equal to 0 when x is equal to y, 1 when x not equal to y. Then the open ball centered at small x and the radius r is given by b of x comma r is equal to when r is less than or equal to 1. The radius is less than or equal to 1, then the only possible value of d of x comma y is 0. That is, when x is equal to y, d of x comma y is equal to 0. Therefore, when r less than or equal to 1, b of x comma r is equal to singleton x. When r greater than 0, greater than 1, then d of x comma y is equal to 0 and 1 are possible. That is, the values of d of x comma y is equal to 0, 1 and 1 are possible. Therefore, in this case, when r greater than 1, b of x comma r is equal to the set of all real numbers. That is, y takes all the values of r. Therefore, b of x comma r is equal to the set of all real numbers. Next, we are going to see the definition of open set in a metric space. Let x comma d be a metric space. A subset G of x is said to be an open subset of x, or more simply, G is open in x. If for every small x belongs to G, there exists a number small r greater than 0 such that the entire ball B of x comma r is contained in G. That is, x belongs to B of x comma r is fully contained in G for every small x belongs to G. Here, small x is called the interior point of G. When G is open, every point of G is called the interior point of G. Some important examples, results. In a metric space x comma d, the following results are true. Both x and y are open in x. Every open ball is itself an open set in x. Arbitrary union of open sets is an open set in x. Finite intersection of open sets is again an open set in x. Using these results, we are going to see few examples of open sets. Let us take x to be the set of all real numbers and d of x comma y be the usual metric. Then every open interval a comma b in R is an open set, since every neighborhood of open interval a comma b is fully contained in G, where G is equal to open interval a comma b. Therefore, all the points of open interval a comma b is an interior points of open interval a comma b. Therefore, open interval a comma b is open in R. Therefore, open interval 0 comma 1 is open. Open interval 2 comma 3 is open interval 3 comma 4 is open interval a comma infinity is open interval minus infinity comma a is open. Right? Next, open interval 0 comma 1 union 2 comma 3 is open. By the third result, union of two open sets is open. Therefore, open interval 0 comma 1 union 2 comma open interval 2 comma 3 is open in R. But G is equal to close to 1 open interval 2 is not open in R, since 1 is not an interior point. Since every neighborhood of 1 is not fully contained in closed 1 open 2. Some part of the neighborhood lies outside of open closed 1 comma open 2. Therefore, closed 1 comma open 2 is not open in R. Next, the definition of a closed set. A subset of the metric space x comma d is said to be closed in X if its complement is open in X. That is, x minus a, x difference a is open in X. Examples of closed sets. Let us take x to be the set of all real numbers with the usual metric. Here, n is closed in R, since R difference n is equal to union of open intervals. We already known that open intervals are open sets and union of open sets is open, which implies R minus n is open. Therefore, n is closed in R. Similarly, every closed interval in R is closed in R, since R minus closed interval a comma b is equal to union of two open intervals. Third example, the interval closed A open infinity is closed in R since its complement is open in R. Fourth example, Q is not open in R since its complement is not open. R minus Q is not open. Examples. Here, let us consider X to be the set of all real numbers with a discrete metric. In this case, by our second result, every open ball is itself an open set, which implies from this result B of x comma r is equal to singleton x when r less than or equal to 1, which implies singleton x is open in R with the discrete metric. But in the case of usual metric, singleton x is not open in R, but R with the discrete metric, every singleton set is open in R. Therefore, every subset of R with the discrete metric is open in R. Suppose if we consider the set set is 0 and 1, 2-point set 0 and 1, which is equal to union of two sets, union of two 1-point sets, namely singleton 0 and singleton 1. Singleton 0 and singleton 1 are open in R with the discrete metric by example, the above example. Therefore, it is the union of two open sets. We already known that union of open sets is open. Therefore, singleton set 0, 1 is open. Similarly, we can show that every subset of R with the discrete metric is open in R with the discrete metric. We denote R with the discrete metric by R suffix D. Every subset of RD is open in RD implies the closed interval A comma B is open in RD, but this is not true for the case R with the usual metric, since A is not an interior point. Similarly, B is not an interior point. Next example, every subset of RD is open, which implies every subset of RD is closed. Therefore, in a discrete metric, every subset of RD is both open and closed in RD. Similarly, every singleton set is both open and closed in RD. Next example, in any metric space x comma d, every 1-point set is closed in X, since its complement is open in X. Next,